Okay, I will announce it. So my today's topic is mathematical modeling of inflammation. It's the question which we studied already during a number of years. In fact, we started working on modeling of atherosclerosis already more than 15 years, about maybe 15 years ago, or even more. And gradually we began to study also some other diseases and some other conditions of inflammations. And all that becomes more and more complex. And I think it's a good time to discuss what we understand or what we don't understand about inflammation and inflammatory diseases. So this is, in fact, the purpose of my today's presentation. I will begin with a short biological background, and then we will discuss what we call now generic model of inflammation, but then also disease-specific model of inflammations. Then I will discuss, it will be already more or less at the end, and it will be quite short, about the interaction of inflammation with some other physiological phenomena, physiological process. In particular, very shortly I will discuss inflammation and chemotaxis and inflammation and thrombosis. So let's start. So first of all, I found in the internet this image which seems to me quite interesting. They show this symbolic schematic man and different places in the body where inflammation can develop. And in fact, I think that probably, I'm not sure, but I suppose that inflammation can concern probably any tissue and any organ in our body. So some of them are shown here, and well, there are some various diseases which are shown here in the slide, accompanied by inflammation. In particular, for example, cardiovascular disease, we understand that it is atherosclerosis. Of course, inflammation plays a very important role in atherosclerosis. But there are many also other, like, for example, different types of cancers. There are some of them here, but I suppose that all types of cancer are accompanied by inflammation. And of course, it's an important topic, and we begin to study it now. Arthritis, well, we studied arthritis in connection with thrombosis, and I will mention that today. Of course, viral infections, and during the last several years, we study in viral infection with inflammation. We discussed, but did not really study, like some other diseases like psoriasis or asthma. But of course, well, each of them has something specific. For example, we did not discuss obesity and inflammation, and I think it's also a very important and interesting topic. So maybe once we will discuss also, we will study maybe this question. So you see, there are many different diseases, and each of them has some from the point of view of inflammation. And this I will discuss, of course, also shortly in one of the parts of my today's presentation. So, yes. So first of all, what is inflammation? Just a very short, quite common description. What is inflammation? It is a response of our organism. By the way, I will check whether I can show. Yes, pointer. Yes, pointer. It's a response of our organism to infection or injury, and it represents a part of the immune response. But there are also some other situations and inflammatory diseases which are not related to injury or infection. It can be autoimmune diseases and some other diseases. We will shortly discuss them. Also, very interesting question about types of inflammation, because and how to classify them. When you type just chronic inflammation, just inflammation, we will in the search engine, you will see many responses, and rather often inflammations are classified as short inflammation and often associated as short is acute and chronic is long-lasting, long in time. So I don't know whether this classification is precise, but at least it gives some idea about these different inflammations that with respect to their time, it can be short or it can be long. And from other points of view, it can be, for example, studying viral infections, and of course, in some other situations, we know that inflammation can lead to cytokine storm. Sometimes we call it excessive inflammation. And again, I don't know. So there are many different things related here. So this classification may not be precise. Another aspect of inflammation is that some of these inflammatory diseases can be self-sustained, meaning that there are no external stimuli, but still this inflammation continues. This is also a very important topic, and sometimes it is related to autoimmune diseases, but I also think that not necessarily, like, for example, obesity is not an autoimmune disease. But still it can be a chronic self-sustained inflammation. So you see, there are many different things. Somehow they are related to each other, but sometimes it can be really difficult to make a precise classification and precisely discuss that, precisely define that. So this is what we are trying to understand now. Well, there are some signs of manifestations of inflammation. I skip that. So, and then well, I will begin discussing this cell and molecular mechanism of inflammation, because this is both from the biological point of view and from the modeling point of view, it is very important for us to understand this cell and molecular mechanism. And I will describe this mechanism taking as example atherosclerosis. Why atherosclerosis? Because we work on it many years. We understand more or less how it works, I mean, how this inflammation develops. Of course, also because it is an important cardiovascular disease. So what happens here in atherosclerosis? There are two main, like we can say, locations. So we consider the artery in human's body, and in the artery there is blood flow and artery wall. For some reason, rather often this is related to LDL, low-density lipoproteins, which penetrate from the blood flow to the vessel wall. They are oxidized here inside the vessel wall. Being oxidized, they become inflammatory agents. They start inflammation. And because of this inflammation, they activate endothelial cells, which are shown here and which separate blood flow from blood vessel. These endothelial cells are activated. There are some receptors on the surface of these endothelial cells from the site of blood flow, and then these monocytes, white blood cells, they roll on the surface of this internal surface of the blood vessel. They come here to the inflammation place. They are stopped by these receptors. They penetrate inside. They differentiate into macrophages. These macrophages, they phagocyte. They eliminate this ox-LDL. All this, because what is LDL? LDL, these are proteins, they transport lipid particles. Their role, of course, is very important in our body. We should not understand that LDL is necessarily something bad. No, of course, they have an important physiological role, but they can be trapped here. They're eliminated by macrophages. When, after some time, this macrophages eliminating ox-LDL, they are full with these lipid particles. They become foam cells. They cannot go outside. They remain trapped here. After some time, these foam cells die, and altogether they produce a lot of other inflammatory cytokines. So we have this positive feedback loop of inflammation. Also, of course, it's not only monocytes, T cells also participate in that. And this is inflammatory part of atherosclerosis. There is also anti-inflammatory part of atherosclerosis because there are anti-inflammatory monocytes and T cells also penetrating here, and they down-regulate production of inflammatory cytokines. So it's a negative feedback loop. Please, it seems to me that some people have microphone on, and there are some noise here. Please, if there is a case, please switch off your microphone. It will be easier for me to continue. So we see here that there is a competition of two factors, pro-inflammatory and anti-inflammatory. This is shown schematically here in this slide. Already we talk here not about particularly atherosclerosis, but this is what we call generic scheme of inflammation, because we take this inflammatory part of these processes, but we don't discuss how it was initiated, by what disease. So it's only the inflammatory part. So in this inflammatory part, what we have here, we have pro-inflammatory macrophages, which produce inflammatory cytokines. These inflammatory cytokines activate, well, it is written here in the endothelial tissue, it's in the case of atherosclerosis, but in general, some tissue, and this activated tissue produce also even more inflammatory cytokines and attract even more M1, meaning inflammatory macrophages. On the other hand, they also initiate influx of anti-inflammatory macrophages M2, which produce anti-inflammatory cytokines. In these anti-inflammatory cytokines down-regulate production of inflammatory cytokines by macrophages and by the tissue. This is really, in some sense, the center of all these processes, which we are going to discuss, and to some extent of all these inflammatory processes. So there is some persistent noise from the audience, like somebody is doing something. Please switch off your microphones. Okay, I continue. Well, so what I'm going to discuss now is exactly this inflammatory part, how it is related with other physiological conditions in our body. So we consider this inflammation as a part of immune response, and from this point of view, we can consider it is acute inflammation because, for example, viral infection or injury or other situations, when they initiate inflammation, it's often acute inflammation directed together with immune response to eliminate this the origin of this inflammation. I call it stimulus, not I, but usually it's called stimuli. And the stimuli, it can be viral infection, it can be LDL, as in the case of atherosclerosis, it can be tumor cells or something else. So you see there are the stimuli, they initiate inflammation, they initiate immune response, and this inflammation and immune response, they try to eliminate this stimuli. And this is, of course, the origin of the stimuli is disease specific. So if the stimuli are eliminated, so the disease is finished, so inflammation is also finished. The injury in large sense is healed, so everything is okay. On the other hand, if immune response and inflammation cannot eliminate the stimuli, so this disease becomes persistent, and it is related to chronic inflammation. So this is the first very important step. We see that this first bifurcation, where we have the difference between healing and acute inflammation, and the absence of healing and chronic inflammation. So in this case, chronic inflammation is related to the fact that these external stimuli are not eliminated. So viral infection is not finished, tumor is still persistent. We have this chronic inflammation, but related to this ongoing disease. Let's go further. And then the next step is that as we know, immune response eliminate, for example, infected cells or tumor cells, but for some reason, which sometimes or rather often is not known, this immune response can begin to eliminate not only infected or damaged cells, but it can also eliminate healthy cells. And in this case, we have an autoimmune disease. On the other hand, inflammation, so this was about immune response, but inflammation itself, inflammatory cytokines can also kill not only, like, for example, infected cells, as happens during viral infections, but they somehow can begin to kill normal healthy cells, and they can lead to systemic inflammation and to excessive inflammation, sometimes called cytokine storm, because killing these healthy cells, there are a lot of additional inflammatory cytokines are produced, and again we have this positive feedback loop. And you see all these arrows I showed here, there are two sides, so all these effects are in both directions. So we see already that we have this quite complex relation of inflammation and immune response with many other physiological processes. This scheme is not yet finished. I will continue it, but right now I will discuss a little bit in more detail this central part of our scheme about this inflammation and immune response from the point of view of this generic model of inflammation. So what we do, in particular with Wissam, with Annotация, with some other people, so we write this generic model of inflammation. So we have this tissue, which can be uninflamed, so uninflamed cells, inflamed cells, and two types of macrophages, pro and anti-inflammatory, and two types of cytokines, pro and anti-inflammatory. I will not describe in detail all these right-hand sides. You can easily imagine that these equations describe production or elimination of all these cells and cytokines, and this corresponds to this scheme shown here. So we started this model. Well, it is written as reaction diffusion equations. As usual, we can begin with ordinary differential equation. Okay, I see equation from, strangely enough, something I can see now on my screen. I think it was equation from Nikolai Pertsov, please.
Vitaly,
yes.
What do you mean by X?
X, you mean in the equations?
In the equations, X.
Yes, I understand your question. Yes, this is what I'm saying, that we write this reaction diffusion system of equations. In fact, here X is just space variable, and here space variable corresponds to real physical space position. So we have some tissue in the body. For example, it can be endothelial tissue in atherosclerosis. It can be epithelial tissue, for example, in viral infections. So X is the coordinate along this along this tissue which we consider. Is this clear?
Thank you. And I would like to see initial and boundary conditions.
Okay. So yes, I understand your question. I don't go here in detail of mathematical formulation because all that is quite standard. Well, I will shortly say. So we can consider, rather often we consider it in 1D formulation, sometimes in 2D formulation. Boundary conditions are usually considered as like no flux boundary conditions or homogeneous Neumann boundary conditions. Initial conditions also depend on the problem which we consider. Rather often, for example, in this inflammation problem, all initial conditions are 0, but we introduce initially some non-zero concentration of inflammatory cytokines, and then we see what happens. So all that is
Thank you.
Quite standard. But just to finish my response to your question, as I say here, we consider x as physical variable corresponding to the coordinate, to the position in the tissue. But in some other problems, and I will not discuss this question today, we can consider a space variable which corresponds to the genotype space. Sometimes phenotype space, sometimes genotype space. This is completely different interpretation, but I will not discuss it today because it would be too long. So for us, X, it's a usual space variable. So we can begin to study this problem considering ordinary differential equations corresponding to this reaction diffusion problem. And one example is shown here. Of course, it can be much more complex, but I think a good specific example is shown here. So here we have x-axis corresponds to this horizontal axis corresponds to one parameter beta, and this vertical axis corresponds to the concentration of one of the variables. In this case, this is a concentration of inflammatory cytokines. So we see that there are different regions. The first region is very simple. There is only one stationary point. It is globally asymptotically stable. Concentration of inflammatory cytokines here is 0. So no disease, no inflammation, everything is good here. And this is called here region 2. The opposite situation is here in region 1. There are two stationary points. This inflammation-free stationary point is unstable, and there is another stationary point which is stable and which corresponds to some positive concentration of inflammatory cytokines and of all other variables. So this point being unstable, even a small, disease-free, inflammation-free point is unstable. So even a small perturbation leads to growth, to the development of this inflammation, and it goes to this inflammatory state. There are some intermediate situations where this inflammation-free stationary point, for example, in region 3, inflammation-free stationary point is stable, and if the perturbation is small, we remain here in this inflammation-free equilibrium. But if perturbation is large, we will go to another equilibrium with inflammation. So usually we call, not only we, of course, the situation bistable. It is important because, for example, modeling atherosclerosis, we often deal with the situation where this disease-free stationary point is stable, but if this initial stimulus, for example, LDL concentration is high, so then atherosclerosis begins to develop. And finally, the last situation shown here, it's region 4, where this inflammation-free point is unstable. There is one inflammatory point stable, another inflammatory point stable, separated by an unstable point. These two stable points, one with low value of inflammation, another one with high value of inflammation. So this is basically what happens here if we consider the ODE problem for this generic model of inflammation. And what I explained here is shown here on the slide about these different regions, different number of stationary points, and the behavior of the problem. Now, if we introduce indeed the space variable, and this is important, and well, truly speaking, I don't try to discuss with medical people anymore, but during a number of years, I tried to do this, and this concept of space propagation of inflammation, I think, is completely just foreign for them. They impossible even to discuss that. But we understand that inflammation can really spread. For example, here you see this is an example. This spots, these plaques on of inflammation on the skin. They can propagate, and we will see below they can propagate in different patterns. And describing that, we introduce this space variable, and we see that, for example, in the example shown here, so we see here all these variables: inflamed cells, uninflamed cells, macrophages, cytokines. For example, here we take this figure, upper right figure, we see this propagation of the concentration of inflamed cells in time. So this is space variable, this is concentration. Here, if we fix one moment of time, it will be this distribution like that, shown by this curve. In the next moment of time, it will be this next curve, the next curve. So mathematically speaking, this is what is called reaction diffusion waves, or traveling wave solutions of parabolic equations. But in applications, this means that the size of this spot grows in time. And there are different regimes of this propagation depending on this our situation with this number and stability of these stationary points. Of course, if our parameters corresponds to region 1, there's nothing happens. If in region 2, in region 1 monostable case, there's transition from this unstable to the stable. In this region 3, for example, 2 stable points by stable case. So there are some differences in all these wave propagations. Well, nothing very unusual here. We discuss it for many different problems. I will not stop on that today in detail. I will only mention here that, well, it's a little bit more special in this region 4, where we have 4 points: unstable, stable, unstable, stable. In this case, we can have this propagation of 2 consecutive waves, as shown here. The first wave, it's propagation from unstable point to stable point, and this is the first wave, and the second wave from stable point to stable point. So there are 2 consecutive waves propagating here with different speeds, and then we study the speeds. If the speed of the second wave is larger, then they merge and form one single wave. If it is slower, they propagate like it is shown here as 2 consecutive waves. And of course, from the mathematical point of view, there are many studies, and we work on such kind of mathematical problems related to reaction diffusion waves for many years. For me, it's, you can believe, more than 40 years. I should not say that. And there are all these questions related to wave existence, wave stability, speed of propagation, different regimes of wave propagation. So finally, there are many mathematical questions behind. I will not discuss them today at all. So this is all about mathematics. So I am more interested today to discuss modeling and our attempts to understand what is inflammation and how it works. And an important part of this understanding, it's exactly the question which we discuss now, is shown here in this slide, and this is related to what is called a resolution of inflammation. How we can return from inflammation to normal homeostasis without inflammation. And clearly, it's an important question, and in fact, I think that only now we are ready, even not to answer it, but at least to give some like possible understanding of that. And we work on this question exactly now, and our actual understanding I will try to explain here on the slide. And again, I will use exactly this model of generic inflammation we just introduced before. And in this model of generic explanation, we have a very important, this participant, this M1, this pro-inflammatory cytokines. So what happens, in fact, when inflammation begins? For example, we can think about like viral infection or some other disease. So So when this when this disease begins, so somehow depending on the external stimuli, somehow these initial inflammatory cytokines are produced, and these initial cytokines attract by different possible mechanisms somehow these pro-inflammatory cytokines. But what is important here, and here we really need to go in detail of this physiological process, otherwise it is impossible to understand what is happening here. And when we study that in more detail, it appears that, again, we talk about different macrophages, pro and anti-inflammatory, but we need now introduce two other types of macrophages: resident macrophages, which are always present in the tissue, and circulating macrophages, which go to the tissue when the tissue is inflamed as a part of the immune response. So we need to understand that. And rather often, resident macrophages, they can also be of two types, pro and anti-inflammatory, but rather often, at least in the literature we just studied, they are associated with anti-inflammatory response, and circulating macrophages are rather often associated with pro-inflammatory response. So what happens when the inflammation begins? These pro-inflammatory cytokines, they enter the tissue, but these cytokines these macrophages have certain lifespan. So life duration of the cells is not very long. It is several days, like 4, 5, 6 days. First, when they come into the tissues, they don't die. So this is an interesting point, because rather often we write our models as ordinary differential equations, as partial differential equations.
Excuse me, Professor Wольperт. It seems like you are unmuted.
And now?
Yes, it's okay.
It's okay.
The sound disappears from rather often. We consider, I suppose.
The problem is that I repeated so many times this phrase that I don't know from which one. But okay.
So it's about the lifespan of circulating macrophages.
Okay, good. Anyway, when we okay, I will repeat this. Rather often when we consider, I start exactly from this point. Rather often when we consider all these models, we describe death of cells with this type of terms, that the death is proportional to their concentration. The problem here is that this description is relevant if we consider long time intervals, long with respect to the lifespan of the cells. If we consider our time interval is 1 year, but life duration of the cells is several days, then it is appropriate. Then we can write it in this form. But if our time interval is several days and life duration of the cells is several days, then it is not exactly, it might not be relevant, because in these time scales, the cells do not die. This is what is very important. This is why not always we can consider these models in this form. So when we consider short time periods, we should take into account that in the beginning, the cells do not die. But after some time, they begin to die. So there is time delay, and we need to introduce this time delay in this particular term of the model. So if we do that, then in the beginning, the cells do not die. And then we have this model, the same model, but without cell death. And if we study this model, we will obtain that the concentration of these inflammatory macrophages will grow, and the concentration of inflammatory cytokines will grow. This is shown here with this red arrow. But after some time, the cells begin to die, and we return to our model with death of the cells, and we can return to our stationary points of this model. So starting from this point, we recall that cells die and we have different stationary points. So where we can move from this point, we can move here as shown with this green arrow, and we will, if this inflammation-free stationary point is stable, so we eliminate completely our inflammation, everything is okay, the disease is finished, the inflammation is finished, so we return to normal homeostasis. On the other hand, for some other values of parameters, it is possible that we will go here to this branch of our solutions, stationary points, and then we have persistent inflammation, inflammatory disease or some other disease. So this is our actual understanding of this important question of resolution of inflammation and return to homeostasis. This is not described. So if we take this generic model shown here, this model does not describe. This is important to understand. This model describes the emergence of inflammation, the development of inflammation, but it does not describe a return to the, how inflammation is finished. This is important. So, but we understand, of course, that we should be able to go both ways, towards the inflammation and back. So, but not in this model. We need to introduce something else, and I explained to you how to do it here. Okay, so now we can complete our scheme here with this rectangle at the bottom. So after elimination of stimulus, we can either return to homeostasis with zero concentration of inflammatory cytokines, or to some inflammatory diseases if this concentration of inflammatory cytokines is positive, and both of them are possible in this, as we saw in this generic model inflammation. So this scheme is now almost complete, and some remarks about that is when we talk about generic model of inflammation, it does not take into account several important things. First of all, as we discussed, the origin of the stimulus. It can be, as we discussed, virus or tumor cells or something else. This we should introduce when we consider this disease-specific models of inflammation. Then inflammation can be eliminated or not. In this case, we have either chronic disease eliminated or not. So I don't understand what I have written here anyway. So the stimulus can be eliminated or not. In this case, if it is eliminated, we have resolution of inflammation, and if it is not eliminated, so we will move towards chronic disease. Also, this immune response killing healthy cells, and when we have this autoimmune diseases, again, this is not described by this generic model of inflammation because we don't put in this model how immune cells kills healthy cells. Again, if we return to this model, so we have this uninflamed cells become inflamed cells, but we don't take into account these uninflamed cells or inflamed cells that they can be killed by immune cells. So if we want to describe autoimmune diseases, we need to introduce here some additional terms. As we introduce here something else to describe return to homeostasis, then we need to introduce something else to describe autoimmune diseases. And if we want to study systemic inflammation and cytokine storm, we also need to introduce something else in this generic model, namely that inflammation can also kill healthy cells, and by that can produce even more inflammatory cytokines. So you see this what we call generic model of inflammation is in the center of all that. But if you want to describe in more detail all these processes, like what all that I just presented here, like autoimmune diseases or something else, we need to complete this model by something else. And another remark, it's about acute and chronic inflammation. This is really very complex question, which we try to understand exactly now. And for example, Annotация sent me this paper, and we need to understand. So how that acute and chronic inflammation, they're different. And this is well presented in this slide. So some of inflammatory cytokines are the same, but some other are different. So acute inflammation and chronic inflammation, they differ from each other. The important question, of course, is from if we consider just molecular and cellular mechanisms, how this transition occurs from acute to chronic inflammation. I'm not ready to answer this question now in this general formulation. If we have time, I'm not sure we can discuss it for cancer, what we do now, but we just should keep in mind that this transition between acute and chronic inflammation, this is very important and this is very complex, but it is possible that there is no really transition. They might develop both at the same time because different molecules are involved in these processes. At some point, some of them can prevail over another one. So we don't know either these are consecutive processes or simultaneous processes and how it happens. So for us, at least, it's an open question, and we try to understand how it works. So now I try to complete finally this final form for today. Every day this scheme evolves. So today I added this chronic inflammation here. Before, chronic inflammation was only here from the left. Now I added it also from the right, showing that autoimmune diseases or inflammatory diseases can also be considered as chronic inflammation. Before, just a week ago, I considered chronic inflammation as related to the diseases which still continue. If viral infection or tumor are not eliminated, this disease all the time stimulates inflammation. This is chronic inflammation. But even if we eliminate stimulus, then these diseases, like autoimmune diseases, they can continue, and they are also considered as chronic inflammation. You see, so in this classification of different types of inflammation and different types of diseases, it's a little bit ambiguous. So there's kind of recurrence between different terminology, but I think that we understand now, at least at this level. Okay, today, preparing once again this talk, I asked Chat GPT what is chronic inflammation. This is also interesting, and it gives, as usual, it gives a good answer, but quite generic, without not very concrete, not very specific. But it's exactly in the lines we discussed now. So this chronic inflammation, it can be related to persistent infections. It can be related to autoimmune diseases. Obesity, okay, we understand that. And some other, this already external factors like environmental factors, diet, stress, things like that. We will not discuss all that. So it becomes, it's already another level of questions. So we stay with here this when we talk about chronic inflammation. We mean these persistent diseases, not only like infections, but it can be, for example, cancer or other persistent diseases. It can be autoimmune diseases. Well, obesity we did not discuss recently, but I think it's also an interesting question, maybe sometime later. Okay, so I have only 10 minutes, so the remaining part will be very quick and very short. Disease-specific models of inflammation. So here, what I showed here, you see these different stimulus, they can initiate inflammation, and then this two-side influence is very important, whether it is stimulus, whether it is eliminated or not. And how it works, it depends on each specific disease. For example, we discussed a little bit atherosclerosis, but if you go in more detail of all this like low density lipoproteins oxidized or not, high density lipoproteins oxidized or not, various types of cytokines, T cells, macrophages, monocytes. So this becomes a little bit more complex, and we discussed it before. I will not stop on that today. Of course, viral infections, and we also studied this last several years, how viral infections provoke inflammation. This is very important. And again, so it's at the same time a part of the innate immune response. Innate immune response then continues with adaptive immune response. This then it can continue with cytokine storm, as we know, for example, last year for this COVID-19 and so on. So we studied all that. So this is a complex interaction between viral infection, immune response, and inflammation. Unfortunately, I cannot discuss it in much detail now. Of course, inflammation plays a very important role in neurodegenerative diseases, and we studied this already quite for a long time for Alzheimer's disease. And here, this stimulus which initiates inflammation, it is related to this amyloid beta monomers with a wrong configuration. With this wrong monomers, there are good monomers, there are bad monomers. This bad monomers, their length is not good because of some genetic changes. They begin to form aggregates, oligomers aggregates, and these aggregates, they are cytotoxic. They kill neurons, but at the same time, they lead to production of inflammatory cytokines, and these inflammatory cytokines increase even more production of this amyloid beta monomers. So again, we see this positive feedback loop of inflammation and Alzheimer's disease, and then it leads to plaque formation and things like that. And when we studied that, we come to a very interesting hypothesis. So that in fact, it's our theoretical prediction is that inflammation can initiate Alzheimer's disease. What means initiate? Because for the Alzheimer's disease, inflammation by itself is not sufficient. The basis, the main feature of the Alzheimer's disease, as I mentioned here, is existence of this wrong amyloid beta monomers. Without that, Alzheimer's disease will not develop. But assuming that they are already present, then inflammation can just push them to the development of the disease. This is possible. Because when we have here, I mentioned this bistable case. Yes, bistable case, disease-free equilibrium is stable. How we can destabilize it? One of the ways to destabilize it, in the case of Alzheimer's disease, is to introduce inflammation. So it can be some inflammation not related to the Alzheimer's disease, but it can trigger the beginning of the Alzheimer's disease. This is the conclusion of our study. Of course, cancer, and this is what we discuss now with Annotация, with some other people. This is really, we found this paper with this beautiful scheme. Of course, we cannot discuss it now in detail. But the idea is that there is this vertical line here, and to the left it's acute inflammation, to the right is chronic inflammation. Acute inflammation is a part of the immune response, and the immune response tries to eliminate tumor. But chronic inflammation, which here is not considered as a long, it's this acute chronic here, it's not the position of short and long. These are just different mechanisms, and probably they can develop simultaneously. So from the very beginning, there is this acute inflammation as part of the immune response trying to eliminate tumor. But on the other hand, there are huge amount of these inflammatory cytokines and other immune cells related to chronic inflammation, and which try to stop immune response. So immune response, normal immune response, try to eliminate tumor. Chronic inflammation tries to down-regulate this immune response. This is shown here in the scheme, which I draw myself. So there is tumor, there is immune response trying to eliminate that, but then chronic inflammation, it promotes, first of all, it promotes tumor growth, but on the other hand, it's different. It down-regulates immune response. So you see how it works. So again, it's about the question, what is acute inflammation and what is chronic inflammation. So I really think that we need to go in more detail of this cellular and molecular mechanisms of acute and chronic inflammation to understand the interaction between them. Well, other diseases, we discussed some of them. So I have only 5 minutes. I will not discuss this. Well, in fact, there are 2 remaining questions: inflammation and chemotaxis, and inflammation and thrombosis. I will only say that chemotaxis really is very important here. And as we understand now, chemotaxis in atherosclerosis, chemotaxis in Alzheimer's disease, and I suppose also in other diseases. So the interaction of inflammation and chemotaxis leads to plaque formation. This is the main conclusion of the several studies we do now and of what I wanted to show here. So let us keep it just in mind that it's exactly chemotaxis with its interaction with inflammation which leads to plaque formation, at least to the beginning of plaque formation, but okay. This is nice. So this is not chemotaxis. It's like what it was just to show you that there are other possible mechanisms, not only chemotaxis. We tried to apply other mechanisms, in particular here related to Turing structures, where the Turing structures can be considered as a mechanism of emergence of these structures in patterns in inflammation. So we got some very close, again, we consider it kind of generic model inflammation. With the modeling, we obtained some results which really resemble a lot real pictures. For example, if we took here at the bottom, so these color pictures are like real photographs, and this black and white, what we obtained in modeling, you see there are different patterns which resemble what we observe here, and some other examples shown here. Okay, it's an interesting question. I think that we see some really, for example, if you look at this number 6 here, you see this cross-like pattern. How you can imagine this cross-like pattern will emerge, and we observe it in model. How it is possible? It's kind of coincidence like that. They show that this is not occasional, but we cannot really prove that, and the model is too simplified, and so we have not even published that because it's not easy to justify all that. But this is interesting. Inflammation and thrombosis is, of course, another very important topic. We studied it's in different contexts for arthritis. Rheumatoid arthritis leads to production of different inflammatory cytokines, in particular interleukin-17 and TNF-alpha, and the common action of these 2 cytokines increases by 10 times the risk of cardiovascular diseases, both atherosclerosis and thrombosis. So here we studied it for thrombosis. We showed how they act to how these cytokines they act on these inflammatory pathways, upregulate inflammatory pathways, leads to thrombus formation, and another cycle of works was devoted to the influence of these inflammatory cytokines in COVID, also thrombus formation. We know that in COVID it was very important risk factors, and we studied that with Anas and Annotacia. I think we have maybe 2 or 3 works, I don't remember, where we see how, for example, here thrombus formation, this red one, without in healthy plasma. This is for COVID-19 plasma. So we see how thrombus becomes larger, and we also studied this thrombus formation in small blood vessels in the lungs. This was an important risk factor during COVID-19 disease. So to conclude, we have the scheme shown here, how inflammation and immune response are related with many other different physiological situations. I think this is really the center of the main point of what I tried to discuss today, how this is related to the initial stimuli, healing or chronic inflammation, to autoimmune diseases, to homeostasis or inflammatory diseases, to excessive inflammation. So this is really related, this inflammation and immune response in the center is really related to many physiological situations, to many diseases. So we really need to understand how it works in the generic setting and for each particular type of diseases. So this is really the message of my today's talk. And then some related question. This is what I also briefly mentioned about spatial propagation, about plaque formation, about thrombosis, and some other. So I think I'm ready to finish. Further questions we discussed a little bit. Yes, there is a number, in fact, many questions related. Some of them we studied, in particular, free boundary problems. We work on that now. This is quite complex. Okay, some references, participants, not all publications here. There are much more of them. Some of them I would like to acknowledge participation of our colleagues, collaborators from РУДН. It's Annotация who is present here, and some graduate and undergraduate students. Also, we collaborate with group from Lebanon, from Beirut, with Nader El Khatib, Gada, and Wissam, all of them either former graduate students or actual graduate students. And also, of course, we collaborate with many other people. I also would like to mention contribution of Anas Bushnita, who is also my former graduate student. He is now in the USA, but we continue to work on all these problems. Okay, I stop on that. Thanks for listening. I hope that it might be potentially interesting and useful. Anastasia, since I don't see the, okay, no, sorry, I see there is a question from Nikolai. Please, Nikolai. No, I don't hear. Anastasia, please answer, because I see some hands appearing and disappearing, so I don't see what is happening.
Nikolai Viktorovich, you are unmuted now. So if you can put on your microphone. If there is some technical problems, we can move to that.
Sorry. I repeat, thank you for the interesting talk. It is a great study and very interesting to listen you. And nevertheless, I have one simple question concerning the model of immune response. Please show the slide with immune response. This question is,
just a minute, I will find. Yes, for example, here. Yes, for example, this one. Yes.
Next slide. Next. Latest, more latest.
Well, I think that I showed also more detailed model for atherosclerosis and showed this simplified model. Yes.
Yeah.
Okay. Yeah.
My question is two variables for first equation for derivative of E with respect to T. And the last term is minus K sub 2 E multiplied by V.
Right.
This is destruction or not. But if we consider the variable for Y, variable Y,
Yes.
I don't see the term minus
Yes, I see.
multiplied by V.
Yes, I see. I can answer. So E here is uninfected cells. E with subscript V infected cells. So you see this similar term appears here for infected cells. But then these infected cells, they produce virus in this equation for V. So in fact, we separate virus production with, I mean, the rate of virus production and the rate of cell infection. These are two different equations.
We have no term minus V with variable V, which
you mean here
with E minus the term that describes the
yes, I understand. Minus E, yes, minus EV here in the equation for V. This is what you mean, right? Yes. I understand your question. Well, we discuss it from time to time, such kind of terms in different models and different equations. For example, when we have cytokines or viruses, do we need to take into account the depletion in such kind of equations? Truly speaking, I don't know, because you know, there's only a very small percentage of viruses which are like enter the cell. So it can be, I don't know, 1 from 1,000 or even less. So do we need to take this into account? And moreover, when they enter infected cells, they don't really disappear, they begin to multiply. So I don't have exact understanding whether we need to write here this minus EV or not, because the most part of viruses, just vast majority of them are not concerned. So I don't know, maybe yes, maybe no. The model becomes more complex, whether it gives something, the addition of this term, whether it gives something else, I don't know. But in some other works, indeed, I think that we have some other works where we indeed take into account virus depletion while it enters cells. Yes.
Thank you, but I don't agree with you.
Oh, this is very good. We are not obliged to be always agree. I understand your question, and in fact I don't mind. Yes, it might be taken into account. Yes, with some small constant. Why not?
Virus penetrates into cell, and sometimes or not.
Yes, of course.
If virus can penetrate into infected cell, then virus disappears. We have no new viruses.
No, excuse me. Here we don't make a difference between virus inside cells and outside cells. In some other models, we make such difference. But if we don't make a difference between virus outside cells and inside cells, in fact, V here is a joint concentration of both of them. So it's not so obvious, because even if it penetrates cells, it does not disappear.
It is a very complex problem, but I repeat my opinion that I'm this very complicated problem, and this model is not good for me, only for me, only for me.
No, Nikolai, I understand your question. I repeat. There is another work where we consider separately virus concentration inside cells and virus concentration outside cells. In this case, I agree that when virus penetrates a cell, it changes its status in some sense from one category, from one class outside cells to another class inside cells. This I completely agree. If we consider virus concentration as both outside and inside cells, then when it penetrates the cell, it does not disappear, it does not change virus concentration. This is my understanding, but at the same time, I don't mind if there are some other understandings. It's okay for me.
Vitaly, thank you very much.
Thank you for your question and thank you for listening.
Okay, then we move to our other listener. Yana, please, you can ask your question.
I want to clarify that the considered model take into account the features of so-called sterile inflammation, the specificity of which is the absence of microbial components which occurs, for example, during organ transplantation.
Well, as usual, you ask difficult questions. So let me go to my scheme here. Okay, so as we discussed before, inflammation can be initiated by some stimulus. The stimulus, if you don't, well, what you ask, if this is not infected, for example, to viral or bacterial infection, if it is not related to oxaldale, if it is not related to tumor cells, then what? Then it can be either autoimmune disease, or it can be injury, or it can be some inflammatory diseases like in obesity. So there are no external stimuli, but still this fat tissue, adipocyte, it is inflamed. So yes, well, if I understand correctly your answer, your question, then the answer is yes, this generic model of inflammation, which we consider here, can take into account inflammation without external stimuli.
Okay, thank you.
Okay, then may I have some questions?
Please.
The first one is about plaque formation. You mentioned the plaque formation while hemataxis. Does it mean the existence of stable waves in the mathematical equations? Or what is plaque here?
Plaque here is instability. Okay, let me show.
So it's not standing. It's not a standing wave.
No, wait. They are both of them. In fact, no, not a standing wave. No. Okay. So first of all, the simplest interpretation is that it's an instability of some equilibrium. We have a stationary point which does not depend on space. It is constant in space, stationary solution. The stationary solution can lose its stability, and in this case, just a minute, I will show. Yes, in this case, we will have such periodic solutions like shown here in the slide. So these periodic solutions appear as a result of instability of this stationary solution. And this instability is related exactly to hemataxis.
So they are not moving with time. Yes.
They are not moving with time. They are stationary.
Okay.
And we associate this like instability with plaque formation. In particular, what we studied, it's another interesting study from my point of view, which we cannot publish for some mysterious reason. When we talk about fatty streaks is the first stage of plaque formation in atherosclerosis. Because when we talk about atherosclerotic plaque, usually people understand a developed plaque, as it is shown in this figure. This is different. The beginning of that, these are very small plaques which are distributed everywhere along the whole vessel. Because these more advanced atheroma plaques, they appear not everywhere. They usually appear in the points of bifurcations of vessels or where there are some other perturbations, and this is often related to hydrodynamic properties of blood flow. But this is a much later stage of the development of the plaque. The beginning of plaque formation, it is called fatty streak. It appears everywhere on the internal surface of the artery. And there are experiments which show, so here this photo, it's not very clear, but this yellow things, these fatty streaks. And there are experiments on mice, very precise. So they put mice, it is called fat diet. They give this poor animal a lot of fatty food, and several weeks after that, they have these fatty streaks. But if they return to normal diet with low fat, these fatty streaks disappear. So this is a reversible stage of plaque formation. And this fatty streak formation is well described by this mathematical model of interaction of inflammation and chemotaxis. And by the way, also this reversibility of this formation of fatty streaks. So, and this is stationary. This does not move in time. What moves in time? If we introduce this chemotaxis or this perturbation somewhere, but better to say not chemotaxis, but perturbation, if we introduce it somewhere in some particular place, then it will start to spread in space. Okay, so again, for fatty streak formation, we say that it's an interaction of inflammation and chemotaxis. So if we introduce this inflammatory cytokines locally, it is shown here, this yellow cell. So what will happen? This inflammation will spread in space. And behind, in this case, indeed, there is wave propagation as shown here in this figure here. There is wave propagation. Behind this wave, there is formation of these fatty streaks. So plaque formation, it's a combination of several processes. It can be considered as stationary, like a stationary plaque formation, stationary solution. But first of all, there is this wave propagation, and this plaque formation occurs behind this propagating wave.
So this is like a stationary point, but not homogeneous in space. Like
well,
this.
it's well. I would prefer not to call it stationary because it's a stationary point, because it is not. But it's stationary structure. Yes.
Okay. Thank you. And we cannot obtain such solutions in system without chemotaxis. Yes. Can we obtain solutions like this in our models for inflammation propagation, for example?
Not in these models, because this instability of this solution is really related to chemotaxis. If we remove chemotaxis from this model, if we remove for chemotaxis, here's this chemotaxis term. You see in the first equation minus this. This is chemotaxis term. It is known for many different problems and studies that such kind of terms can lead to the instability and to this pattern formation. So if we remove it in this model, there is no instability, there is no pattern formation. However, as I briefly mentioned, There is another mechanism of pattern formation related to Turing structures, which we consider here. What in Turing structures, there is no chemotaxis, but there is diffusion with different diffusion coefficients. So here in the simplified model, we consider only inflammatory cytokines called A, anti-inflammatory cytokines called B, interaction between them, and diffusion of them. And this simple model can give this pattern formation, plaque formation. But what is important here is that one of the conditions of this pattern formation is that this diffusion coefficient should be different. It never occurs for the same diffusion coefficient. At least 2 times or something like that. So they should be different. It depends on parameters. Then the question is how to justify this biologically. If we consider inflammatory and anti-inflammatory cytokines, do they diffuse in the same way or in a different way? And when we did this work, I really tried to show that this can be different, that the diffusion coefficient can be different. Why they can be different? Because they are different. These are different molecules, and their diffusion depends on their size. And usually, according to what I found, inflammatory molecules are smaller than anti-inflammatory. No, sorry. What? Yes, yes. Inflammatory molecules are smaller and diffuse faster. So whether it is sufficient or not to produce the structures, I cannot say.
Okay, thank you. And one more last question from me. You said about the consecutive waves in one case of inflammation, where this is like
Yes.
wave followed by the wave. How? What is the meaning of such a regime from the biological point of view? How can we interpret this?
I don't have precise answer. I can give you some suggestions to think about. This inflammatory disease, for example, can begin as acute inflammation and then continue as chronic inflammation, for example. Or it can begin as low-grade inflammation, meaning that inflammation is weak, and then for some reason it goes to higher level of inflammation. So these are possible explanations. I cannot say, I cannot confirm this by some experiments or clinical data.
Okay, thank you. We have one more raising hand, but I'm not sure. Nikolai Viktorovich, are you have more questions or you just not left it raised?
Anastasia, repeat your question.
Do you have more questions? I see your rising hand still.
No, my question was.
Yeah. Okay. So I think no more questions. It's just
Okay.
No question.
Okay.
Indeed, I have many questions, but
it's very good. So we'll have interesting discussion.
We will have a very interesting discussion because one of my question concerning the well-posedness of all the models because we have non-linear partial differential equations, and there are many, but Vitaly said that we don't discuss this in this talk.
I can give a very short answer.
No. It is very interesting question to discussion. If we will meet you, if in Moscow in some future months, it will be interesting to discuss. But,
yes, of course. But expecting our discussion, I can give you some element of the answer. And this is that if we consider reaction diffusion systems of equations, then the question of well-posedness, I mean, is like conventional boundary and initial conditions, things like that. So no problem with well-posedness. So every existence of solutions, uniqueness of solutions, all this usual mathematical.
Problem
positive, of course, positivity of solution, boundedness of solutions, all that is proved. And of course, there are many different models, but I mean, these are conventional equations, and for every model, we verify that the solution is positive, solution is bounded, solution exists, and so on and so forth. Where it becomes much more complex, it is if we introduce chemotaxis. So because there is this derivative, like this, I mean, with respect to second derivative with respect to another variable, this becomes and such, so it's like cross diffusion terms. This becomes much more complex, and in fact, the solution may become unbounded, and the whole mathematical literature about these blow-up solutions and things like that. So it's a complex question, and indeed, we need to discuss it. Like
models are very complicated, complicated. We will study. We study more simple models, but we study compartmental models. And we study transition of cells and viruses, transitions between several compartments, and we use delay equations.
I understand that. Sometimes we also use delay equation, and I briefly mentioned that, but it's another big topic. I see another question from Daria Evgenievna, please.
Vitaly Aizikovich, I have not a question concerning mathematics. I have for you and for Nastya some questions with organizational nature. Could we talk a little bit direct after the seminar, if it's suitable for you?
Yes,
it's a question for Anastasia or for both of us?
For both.
Okay, we will do that.
Okay, thank you.
Well, if no other questions, then I think we can